So, so without further ado, let's get into the uh, meat of what I want to discuss is firstly this. So we nowadays, if you're following the media, social media, like robotics is really the, I would say, the forefront of where like a lot of smart people are putting their minds into, and like we are seeing really amazing progress, especially let's say last 2 years. So all of these videos that I'm showing here are actually from like last 2 years, and 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 they is there a question?
No, no, we're trying to increase the window, but didn't work.
Okay.
You can go ahead. Sorry.
Okay. Okay, here. So here I am showing like some of the videos from, let's say, physical intelligence or um, Toyota Research Institute or Dyna. There are like startups like Dyna, and there are like big companies like Google, NVIDIA, who are doing robotics, and then they're doing robotics in people are doing with building models with arms, like here physical intelligence and TRI, and then people are also building like humanoids, like Figure, NVIDIA. So there's like a lot of progress, and some of these things we could not imagine um, to do a couple of years back. Um, so like having any zero shot capability, or like having systems that can work for 24 hours straight, like in case of Dyna. So these are some of the things um, that were really 2 years before we didn't have the proof of life, but now we have proof of life for a lot of things that I'm showing here. Although it doesn't, I would also tone down a bit. It doesn't mean that we could, uh, these are ready to deploy systems. Um, so there is still, let's say, a long way to go for these systems to go from like demos or videos to ready to deploy. But still, there is no denying of the fact that the rate of progress has been very high. So that would be like my take home. And now like what is the underlying thing? Why is there this progress happening, right? So for that, let me first go towards a bit of background so that we can get a sense of like, okay, and we can trace out what is the underlying technology behind a lot of this progress. So like if we think about it, since one of the critical elements is LLMs. So I wanted to go a bit, just explain what LLMs is so that it will help you understand later of the what vision language action models are. So LLMs, if the simplest thing to understand here is that they are auto-regressive systems, and that at each time step, they generally decode one token at a time. For example, the if you give it the input the dog, then the next token it predicts, or it gives you a prediction that it's sat. And then why it is autoregressive? Because then that sat is then fed to the LLM itself to predict the next thing, uh, as in time step 2 as down. So now we have four tokens, the dog sat down, and at the time step 3 we are predicting the end of sentence token. So then our final complete prediction is the dog sat down. So so the takeaway is that these LLMs, they predict one token at a time. So this is the fundamental uh, principle behind LLM, this auto-regressive prediction. And what they are trained on a lot of data to do this one-step prediction task. So if someone can do this prediction very well, they kind of they understand the semantics of language, the grammar of language pretty well. So that is how large language models are trained. The thing for us to remember is that they are trained in this auto-regressive manner, um, where they are predicting one token at a time, and then whatever they are predicting is fed into next time step. Right? So that is how LLMs would work, and they are trained on large amount of internet scale data for this task. Now we have LLMs. Then the other thing is vision. How do we add vision to this model? Let's say somehow we train an LLM, the autoregressive LLM. How do we add vision to it? Because like the text, only text input and only text output is not something that is sufficient. We need many a times we need vision, especially for robotics. We want the LLM to also see the world. So we need some vision there. And how do we add vision to an LLM? So we first start with an LLM, and then along with the text tokens or the text words, whatever, there are also image tokens. And how are these image tokens created? So these image tokens are generally come from some vision encoder. And then we fine tune this LLM to now take this text token, take the image token, and then predict some other text token. So then we can do things like question answering. So we can give it the image tokens, we can give it a question, and then we can ask it to predict the answer as text. Okay. How do we create a VLM? Then we fine tune the VLM. So we fine tune the LLM and also the vision encoder and everything now to predict text. So essentially we start with the LLM as the backbone and then introduce this new notion of text tokens. And that is how we train VLMs. Okay. Are there any questions, like high level questions about LLMs, VLMs?
Yeah, any question? No, that's good.
Nope. Okay. Great. So now one more thing which is like aside, and you might have heard this thing called diffusion models a lot, which are like a different kind of techniques, which is also I think useful to understand here. So I'll give a very high overview. So diffusion models are a class of generative models, right? So what are generative models? These are models which can be used to generate something that is their um, they create something from noise, or like they create a new sample. So they would, let's say, generate a new image, right? So these are a class of models that generate something. And how is this specific families of specific type of generative model, that is the diffusion model trained, is that you take a sample from your data. So you have a data set, you take a sample from that data set, and then you keep on adding noise to it one at a time. And at each time step, you have a neural network that predicts the less noisy version of that sample, right? So you have trained a neural network that does this denoising, right? So it will take a noisy sample and it will predict a less noisy version of it. Let's say you have a neural network that does denoising. Now, during generation, if we start with the complete noise input, right? Um, and we have this, let's say, perfectly trained model that can take a noisy input and denoise it, then we iteratively apply that network. So if we start with complete noise and we iteratively apply that network, and it will produce a sample, a new sample um, uh, that it may not have seen in the data directly, right? So that's like the process of a diffusion model. So we have the forward process where we take samples from our data set, keep on adding noise to it, and then ask a neural network to predict a denoised version from a noisy input. And then during generation, we start with complete noise. Randomly, you can generate noise randomly, right? It's just a Gaussian let's say a Gaussian, you could sample something from Gaussians, and then you can create a new sample from it. So these are a class of generative models. Essentially, the takeaway just to remember is that diffusion model is a generative model, and it could be used to generate something from your data. Generate something that looks like your data, right? So those are the things we need to know here. Okay. Now, so those are like the three things we need we used to we needed. We need to know what LLMs are. We needed to know what a VLM is, and we needed to know what is a diffusion model or what is a generative model. And hopefully I've given like some perspective on what they are, and we can now go more deep into understanding what VLAs are, which is like vision language action model. So just like language LLMs power language understanding, and VLMs have both vision and language, VLAs are trying to extend it to also actions, right? So what VLAs are doing is that adding, you already have vision, you already have language. How do you also do action prediction, or like how do you also make that model understand actions? Because it is actions that we care about, that we need for robots to move. We need to know how to move the arm or something, right? um, the how do so as you can see the progression from an LLM to a VLM, there is also a progression. How do you go, let's say you have the progression from VLA, from VLM to VLA is a bit unclear. Now, the question is, how do we build a VLA given we already, let's say, have a VLM that can do question answering, understand images and text. So, so people take different approaches towards building VLAs given a VLM, and based on the approach they take, the VLAs can be classified into three categories that I classified here. So the first category is discrete token VLA. What is a discrete token VLA? So, so what, just as I said that we introduce special tokens for images, we can also introduce special token for actions. And what this discrete token VLA do is, for example, let's say your action can be anything between -1 to 1. Okay. Let's say your robot has a one-dimensional action space. It can only go in one dimension, and the action value can be -1 to 1. What this discrete token, what we will do in the discrete token VLA is that from -1 to 1, we will divide it into, let's say, 10 bins, 10 bins that we define. Okay, so it will be, let's say, -1 to -0.9, -0.8 or something, right? So these are we define these bins, and now we create these new tokens, and then we keep on fine tuning our LLM to now predict these tokens. So let's say given an image and a text, if we want actions, then the VLM, then we train this model to predict these new tokens. So that's would be like a very high level idea of what discrete token VLAs are. The second class of method is the generative model, or like generative head VLAs. So if you just as we were discussing this diffusion process, right? This diffusion action denoising. So one other class of method which is very popular is that you have your LLM. Now you also add a new architecture or a new model that is only predicting actions, and it is predicting actions using this generative process, which is the diffusion process. And how is it doing it? It will take let's say some features or some hidden vectors from your VLM, right? And then it will, based on those hidden vectors, it will do this denoising process, which I was describing before, to create this. It will to create this action value. Um, it can be it can be unclear what exactly is happening here, but then it's sufficient for us to remember right now is that we have a LLM VLM and then we add a generative head on top of it. So that is why these are called generative head VLAs. Okay, that's what we need to remember right now. And then there is a third category of VLAs, which are these custom design VLAs, which they have like uh, some more custom. Yes, please go ahead with your question.
Am I audible?
Yes.
Yeah. Hi. So this discrete token VLA, I'm assuming the output of the model is the tokens, like the action tokens, and then in the generative head, the VLM is separate from the action expert tokens, right? Like, is it inside the same model or are they
Yes. Yes. That's you're right. So here in the discrete token VLA, it's the LLM itself is predicting the token. So there is no new network introduced here. And in the action expert one, we are adding this new network, which is this action expert, and that itself is a diffusion model.
Okay, so like I can consider the action expert in the second case as like a decoder sort of stuff.
Yeah,
Like
it's a decoder, which is specifically a diffusion process decoder or a flow matching. To be like more specific, it's a lot of people use flow matching, but you can almost think of it as like diffusion process here.
Oh, got it. Thank you.
Okay. Good. So, and then, so I was talking about the custom VLA. So apart from these like general strategies, there are also people also do like custom strategies. So these are not necessary for us to understand. But here I've given like one example of like people try to do mix and match inside the VLM itself and stuff like that. So those would be like in the custom category of VLAs. Okay. Okay. So now,
Ankit, I think there's one more question from the
yes.
chat. I see many action icons on the figure. So do VLAs generate a series of actions over multiple time steps or just the one action?
Okay. That's a very good question. So here, um, the VLA could, so let's say you are you are using the SO100 arm, right? And SO100 arm has 6 degrees of freedom. So you would have to predict 6 numbers for the SO1 to move the SO100 arm, right? Now, in order to predict the 6 numbers, you would need 6 tokens, right? So you would for even for one time step, you have to predict multiple tokens, right? So let's say you predict 6 tokens, and sometimes you also not only predict the action of the current time step, you also predict some actions in the future, right? So let's say you predict, generally people will predict action for 8 time steps for many reasons, for efficiency, for better performance and stuff like that. So then you would have to predict 8 times 6, 48 tokens. So then, so generally you would always have multiple predictions, multiple autoregressive prediction from the VLM. Yeah, does that answer?
Thanks. Yes. I guess this is also related to how do you represent the action, right?
Exactly.
I saw some people use joints, some people use and effector pose. Then
Exactly.
the action token will be different.
Exactly. Exactly. So what I was saying was like one example of the action, and there are like delta poses. There is like many different velocity predictions and others. Depends on your hardware and whatever action space someone chooses.
Thanks.
Okay, so now I have given a brief overview of these three categories. Now let's dig a bit deeper. So how do these discrete token VLAs work? One example is here Open VLA. It's a very popular model. So what they do is now you have to create these new tokens, right? So these new tokens are essentially your the action tokens. So either you replace or modify. The VLA has only the LLM has a fixed vocabulary, right? Vocabulary of words. Now you either have to replace some of the vocabulary or introduce this new vocabulary to represent the action tokens. So that is a one modification you would have to make when you create this discrete token VLAs. And what it does is that it compromises because the LLM is pre-trained to predict some tokens and it has a pre-trained language understanding. Now, if we play around with the vocabulary of the LLM, it can create issues. Like it can lead to the LLM not understanding language very well and things like that. So that is an issue that happens when we do this discrete action VLAs. And the other issue is that it has limited resolution um, because you are discretizing your action space, right? So it will always have limited resolution. Now, if we look into the generative head VLAs, what they are doing is that they don't have these issue with limited resolution because they are predicting like floating point values. However, it introduces this new component, as I was talking about earlier, that this action expert is introduced, which is not a pre-trained model. It is trained from scratch just for predicting actions. So this model does not have a lot of generalization because it is trained from scratch, and it's like a new model. And the other thing is like since you're using using the vectors from the VLM and then fine tuning the VLM, it also reduces the language understanding capability because if you think about it, the LLM was originally predicts vectors for predicting text, but now these vectors are used for this diffusion process. So these vectors um, have completely different meaning. And now if you fine tune your LLM to produce these vectors, this often leads to LLM deteriorating a lot on its language understanding capability. Okay. And then the third design, the issue with the custom VLA design is that it is often more complicated and that involves significantly more architectural changes. So here I've listed two designs. One is called Pi Zero Fast and OpenVLA OFT. But that's the issue with these, like some of the custom design VLAs. So some of the limitations here. So all of the architectures have some limitations across different categories, right? Um, one given all these VLAs, one other category of VLA we can think about is what we call hierarchical design. So currently everything we had was a monolithic design where there was just one VLM, right? What a hierarchical design does is that instead of directly predicting actions, uh, we split the task into two parts where the VLM is doing what it is best at doing, and we introduce a new policy where the policy is doing what it is best at doing, right? And this is the design we call hierarchical VLAs, and where we have um, where we leverage the strengths of both the VLM and then and then any policy, specifically here 3D policy. And I'll explain later why we use a 3D policy in the coming slides. But the takeaway here would be, instead of directly predicting action, we separate the process into two parts, where the first part we predict some intermediate representation, and in the second part we use that intermediate representation to predict action using a very specialized policy for that particular task. So that would be the hierarchical design. And one example of this hierarchical design is hamster, is one of the methods, the one of our works that I'll go a bit more deep into. So this, yes, go ahead.
Hey, I have a question on the action conditioning. So are the action more dependent on the vision or on the language?
You're talking about the generative head.
In general for the VLAs.
So they are dependent on both. For it's
No, I mean,
because
yeah, please go ahead.
because let's say we are looking at the discrete token VLA, then you have the tokens from both image and the text and predict actions.
Yeah, what I meant was, for a given same image observation, if I change the text, are the actions going to change too much, or will they be more similar given the scene?
Oh, you mean like in terms of, so that depends on your, ideally for the ideal VLA, it should change depending on both, right? But like for some specific VLA, it could be that they are more dependent. There could be like bias in some specific VLAs, right? But ideally, it should depend on both.
Got it. Got it. Yeah, thank you.
Thank you. Okay, so now let's talk about hamster, this hierarchical design. So this is a quick video that explains this. So let's say you have a VLM. Let me just pause here. So instead of predicting the complete action, what in hamster we do is, like, let's say your task is put M on Mona Lisa. Then the VLM is already good at answering questions about the text. So instead of predicting the entire action, what it predicts is this series of, let's say, a series of floating point numbers here, right? And what these numbers are actually points on the image space. So here, this point 0.79 or 69 would be this point on the image space. So essentially, instead of directly predicting actions, what the VLM is predicting is this 2D trajectory of what action to take. So here the 2D trajectory is, there is a point on the M block, and then there is some intermediate points, and finally there is some point on Mona Lisa here, right? And the change of color is denoting the order in which these points are predicted. And the VLM is also predicting whether at that particular point you should close or open the gripper. So this is an intermediate representation that the VLM is predicting, and it's directly predicting it in text. So the VLM itself is not predicting the action, but this intermediate 2D trajectory as its output. After that, as I said, we can, instead of using the VLM, we can use a very specific policy. So here we use a 3D policy. So we can also add the depth observation here, which takes in this intermediate VLM prediction. And now for the 2D, now for the policy itself, it doesn't need to know what the actual text was. We can replace the text with pick up object and place it somewhere. So it does not need to know all the generalization or all the knowledge about what is M, what is Mona Lisa, right? And then the policy itself could just follow what the intermediate what the um, what the VLM told it to, and then just pick up the object that is identified here. So in some way, we are taking away all the reasoning and all the knowledge task to the VLM, and the 3D policy can now use that intermediate prediction, and it can use any more sensor information like depth and stuff, and then predict the action. And these, since these 3D policies are made to work with, let's say, depth, they work really well, and they can be trained with very little data as opposed to directly training the VLA in a monolithic fashion. Okay.
Ankit, one question here.
Yes.
If you always use this text, like pick up something and place it somewhere, then will the VLA be limited to pick and place only? Can you do other tasks?
Good question. So here, this is just for this particular example that we use this text. Uh, Depending on the example, we have like a category of task. So the LLM, so we have an LLM which classifies whether the task is a pick or place, whether the task is push or something, and then the policy can do all those category of tasks. So it can do pushing objects, it can do opening drawer and things like that.
I see. That makes sense.
Okay. So now in Hamster, how do we train this VLM? So the VLM is actually doing a lot of heavy lifting, right? Because it's understanding the knowledge and it's predicting the points. And how do we train it? So I think the key component here would be like, how do we assemble this training data? So we assemble this to train this model. We assemble data from variety of sources. So we have firstly a lot of data from pixel point prediction tasks. So this would be like, for example, these would be tasks where the VLM has to just uh, predict boxes or pixel locations, right? So for example, find all instances of the question. So then it will answer in text the location of different questions, or it can have question answers like locate the object between the marked items. So it would answer that. So it has this. So we call such question answering task as pixel point prediction task. So we have a lot of such data. Sorry. We also have a lot of vision question answering data. So because we want the VLM to retain its language understanding, so we have like, what is the person feeding the cat? This visual question answering data that already the VLM was trained with it, but we want the VLM to retain that knowledge. So we also additionally, along with our other data, we also train it with this VQA data, visual question answering data. We have like a large amount of simulated robotics data, which has the same task as I showed before, where the VLM is predicting this trajectory, right? So screw the green light bulb, so it has this trajectory prediction. So we have a lot of such trajectory prediction task in simulation. It has like it has a lot of data, but it lacks visual diversity here. And then we have small amount of real world data, because real world data is much more expensive, and our real world data is small. So we have small amount of real world data with this trajectory prediction task for the VLM. And because we have all this kind of variety of data, we find that the VLM itself is very robust. So for example, one of this robustness is like robustness to camera angle, which we get directly by the VLM, but it is very hard to, if you build any policy, it will not work across camera angles if you have not trained it like that. But here we directly get such kind of generalization out of the box. For example, here the task is pick up the M&M and put it in the cup. And if we just rotate around our camera, we see that the predictions are reasonable. Across views, it's giving reasonable predictions about the VLM is giving reasonable prediction. There's nothing about action here. The other cool part about yes, go ahead.
I have a question about the vision data that you're using. So is it egocentric or is it from a third person point of view?
So it has like all kinds of data here. So there is like egocentric, there might be some egocentric VQA data. And there is definitely third person robot data. There might also be like robotics data where the camera is on the wrist. So there is a mix of data here.
Got it. So during real world exhibition, when we have like an extremely different camera angle that it hasn't seen during training, if we don't have enough data of the third person view, will it still be able to generalize to that scenarios?
So so it so this one generalizes because it does have like all the variety of data, right? And it is using a pre-trained VLM, which has a lot of data, lot more data than we fine tune it on. But if you are seeing a scenario where you only train on, let's say, one kind of data, then it would be hard for it to, let's say, generalize to other kinds. So for example, if you just train on third person, then it will not generalize on egocentric and the other way around.
Got it. All right. Thank you.
And here the training is basically supervised the training, right? You have input and the trajectory as output, then you train with supervised fine tuning.
Exactly. So here it is just trained with supervised fine tuning with a variety of different data sources.
Thanks. There's one more question in chat. Looks like the output follow different grammars for different tasks. Do the VLM implicitly classify the underlying tasks to format the output? I think the question is about different tasks.
I see here.
Right, VLM somehow classify these tasks.
Okay.
And
That's a good question. So here, the format is the format is specified in the along with the prompt. So this prompt is not kind of complete here. So here, let's say screw the green light bulb, and there will be additional like predict it as a trajectory, or for example, find all instances and predict it as point. So there will be like an additional because during input we know what kind of output we want, so we can just add that additional thing in the input.
Thanks.
Okay, great question. So now one other cool thing out of this VLM is that it which we found very surprising is that it gives you this way of transferring from sim to real without having any explicit data. For example, let's say I showed you that there are these tasks which we only train in simulation for the VLM, right? But so here there are two of these tasks. So put the cup in the cup holder or screw the light bulb, and this is the only kind of data we had while training. However, since the VLM itself has seen other kinds of real world data, and it has not seen specifically this kind of real world data, it can still transfer to real world in zero shot. So for example, here, even when we give it real images, it can do these tasks and give reasonable prediction. So this is a way of doing. So VLMs. So one way to think about it is that VLMs are able to combine knowledge from different domains, and then use that knowledge jointly. For example, it is able to combine its knowledge of predicting trajectories for this task and its knowledge of just real world in general, right? And then it can use both of these knowledge to do prediction in real world in zero shot. What's even more surprising is that the VLM itself has many other capabilities. So for example, it can understand sketches. And here it is able to even if we give it a sketch as input, it's able to transfer that knowledge. So even on the sketch, if we give it a, instead of giving a real image, we give it a sketch and it will make reasonable predictions on the sketch. Which is a kind of generalization. It would be pretty hard to see otherwise, right? In terms of performance, I will not go very deep into it, but we find that this hierarchical design is better than either using just the policy or just using the either using like a monolithic policy like OpenVLA or just using like the 3D policies. Okay. And what are the kind of failures that we see here? So there are like three kinds of failure that we generally see. Either there is a VLM failure. For example, here the failure is at the VLM level. For pick up the Pookie and put it on the pan, it's selecting the wrong object. The other kind of failure that we see is failure to follow the trajectory. Sometimes, let's say the VLM prediction is correct here, like pick up the right object and put it on the left bowl, but the 3D policy fails to follow it. And the other kind of failure that we see is that the VLM prediction is correct and the it is following the trajectory, but still sometimes the action prediction. For example, here it was going to pick up this object, but it missed the object prediction. So these are the three kinds of failures. And I think for us, it's sufficient to know that there are all these three kinds of failure that can happen for this VLM, for this kind of method. Okay, so we are at 46. Okay, I'll wait a couple of minutes to take any questions that you might have for the hierarchical design and in general anything till now, if there are any questions.
Do you have questions about the? I have one question about how to train the 3D policy. Can you talk a little bit more, like once the policy takes the 2D reference, how does it actually generate the 3D action?
3D actions, exactly. So that I'll cover in my next slides.
Oh, the next. Okay.
Thanks.
How about? Yes, there's one question.
Okay.
Well, what is the base model for the VLM?
The base model for VLM here is called VILA, VILA from NVIDIA. And there are also questions from Jia Hui.
Oh, hi. So my question is like, if there are more than one candidate from the VLM, is that possible covered in the experiment?
Yeah, so the VLM, if there are more than one candidates, it's only predict to, it's just like in language prediction, right? There could be like multiple possible options, but you only predict one of the options here. If you need one prediction here. So similarly here, it will predict one of the options. If you sample again, maybe you can get a different correct trajectory or a different variation of the trajectory.
Okay, thank you.
And another question from Sai.
Hi, my question is about the out of distribution task. Will it still be able to handle that it hasn't seen during the training? Like a completely different task requiring a new skill?
So if it's a hard thing to say, right? Because if there is some task which can, let's say, for example, combine the information and it can do it, then we have some hope. But if it is something that is completely new concept that it has not seen in any kind of data, then it will not work, right? But if yeah,
just a quick follow-up question. Let's say if I want to fine-tune the model for a new task, what should be the balance of the training data? Because if I take too much of training data of that task, I might forget the previous skills. So what's the balance there?
So this is like you have to empirically test it. And the way would be to prevent this forgetting is to when you're training, keep old data in your batch as well.
Okay. Got it. Thank you.
Okay. So I'll quickly go over, and the one more thing would be like, there are also other methods while we publish this work that have also pretty popular that use this design nowadays. So for example, the Hi robot from Physical Intelligence, Groot from NVIDIA, or Helix from Figure Robotics, they are all use some kind of like this hierarchical design policy. Um, so I'll go very quickly over the 3D policy part. Um, uh, so I can go till 20 more minutes, right?
Yes, 25 minutes.
25 minutes. Okay, that's great. Okay, let me quickly go over the 3D policy part, because let's see how does this 3D policy work, right? Given the VLM prediction. So the 3D policy um, can take the scene depth, and so because they are specialized policies and they require very few demonstration to train. And one of the 3D policies that we use here was this work called RVT. Um, and I'll explain how it does its prediction. So one of this policy is very robust, and like for example here it can solve multiple of these tasks with just 10 demonstration each task. So that is why this hierarchical design is useful, because we can have this very specialized policies which require very few demonstrations. And how does RVT work? So I'll give a very quick overview. So you have, let's say, given you have an instruction and a scene, right? For example, here the instruction is stack the teal blocks, and you can see there are multiple teal colored blocks on the table. It's a 3D policy, so what it takes is like it can take single or multiple RGBD images. So you will have RGB and depth for all of these images. And you also have like calibration, camera calibration for all these images. So since you have the camera parameters, what we can do is reconstruct the point cloud of the entire scene. So here, given all these images, we reconstructed the entire point cloud of the scene. Okay. Now, given this reconstructed point cloud, the trick in RVT or this RVT policy is that you can instead of using the original camera images, we can create these camera images, which are virtual images, because given a point cloud, we can always re-render the point cloud from very specific views, which are informative and gives more information about the task. And also they are fixed views. So for example, here we use the direct top view, the direct left, right, and front views. And we use these virtual views now for prediction. Firstly, given these virtual views, what we predict first is like 2D heat map of the next action. So for example, here, stack the teal block, you can see there is a heat map of like all the locations where the teal blocks are, right? Across all these different different images, and this is predicted using like a similar to an LLM, or like a transformer, which takes all these images and predict these heat maps. One thing to note is that these predictions are multimodal, right? So since there are multiple teal blocks, it predicts these multimodal predictions because there are multiple options of which block to pick up first. Now these predictions are in 2D. How do we go in 3D? Is that we take these predictions from different views, and then we average the prediction for each 3D point. So this operation is kind of reverse of the first operation where we were given a point cloud creating the image, but now here, given these like 2D predictions, we are predicting 3D predictions. And these 3D predictions will also have multiple modes here. So for example, here there are these multiple modes of predicted where the gripper should go next. What these predictions mean is the location of where the gripper should go next. Okay, so that is the action space here. So our action space is the 7 degrees of freedom, where 3 degrees are for the location of the gripper, 3 degrees are for the rotation of the gripper, and 1 degree is whether the gripper should be open or closed. So we can get the location of where the gripper should go by using this 3D predicted point, like the point with the highest heat map value. In order to predict the rotation and whether the gripper should be open or closed, what we use is we used features from these locations. So like when the transformer is predicting this heat map, it's also predicting a set of features. So we use the corresponding feature from these locations to predict the rotation and the state, like whether the gripper should be open or closed. And then we execute our action to that next point. So here it's not like a continuous policy. It's predicting these things in jump, almost as waypoint. These are also called waypoints. Essentially, the next high level point where it should go, right? And then we simply use a motion planner to go there. Now wherever our robot ends up, we again feed it to the scene and go through the process again. So this process keeps on going. Okay. So for example, here it predicts it has picked up that one of the teal blocks and moved it there. Okay. So this is the pipeline of RVT, which is one of the 3D policies. Essentially in in our hamster work, along with the current image, we also in that image we give it the we superpose the 2D locations. We superpose the image of the 2D locations that the VLM has predicted. Okay. So in that way we use.
Ankit, I have one question.
Yes.
Since your action is the gripper location and the states, so the heat map, the mode of the heat map may be in some empty space, right? That's where the gripper should go.
Mm-hmm.
It's not always on the objects.
Yes, it can be an empty space. Yes.
I see. Thanks.
Yeah. Okay. And then there is one more work that I'll quickly talk about. Just one slide is RVT2. So we extend this RVT 3D policy to do this multi-scale prediction instead of doing just one scale prediction. Instead of just taking virtual images from the fixed location, we also take, let's say, make a prediction and then take virtual images from that location and refine our prediction. And we find that by using this strategy, we can create very precise policies which have like millimeter level accuracy. So here we have these 3 tasks, and we can see that with just 10 demonstrations for around each task, we can do some of these tasks. Great.
Okay, we have 10 minutes. Then let's
Okay.
try to finish in 10 minutes.
Yes. Okay. So we are okay. So we covered RVT2 multi-scale design, and then in 10 minutes, let's cover like the simplest design that we call VLA 0. So essentially, why to go through all this pain of either creating these new tokens or like creating this generative head or this hierarchical design, why not just predict actions as text? What I mean, predict action as text, I'll explain later. But essentially, what this simplest variation is saying is that we directly use the VLM itself. We don't change its vocabulary. We don't add a new head, and we directly predict, use the VLM as it is. So there is no modification to the VLM itself. And does this baseline work? Like how does this even, like that? The question we ask is how well does this compare to anything else that we do? And that is that we call the simple VLA design, and this particular name would be no modification VLA or VLA 0. So this is a very recent work, which is called VLA 0. It's like building state-of-the-art VLAs with 0 modifications. So as I was saying, here we ask the VLA to predict directly actions as text. So there is no change in tokenization or no new architectural component. And the cool thing here is that we ask the VLA to kind of predict directly let's say here the numbers, and then feed it to the model. And here the training recipe is the important thing, and I'll not go into detail about it here, but the design is pretty simple. Now the question is, so maybe one thing I'll talk about here is that when I'm saying that we are predicting actions as text, the text itself is this set of separated numbers between 0 to 1000, where we, given our initial action space, we convert those floating point values into these integer values, and that serves as our okay. How well does it perform, right? The cool thing is this very simple design is actually better than all other architectures, including some very popular ones. All architectures, including Pi 0.5 or small VLA or open VLA or FT. So these are very popular methods. So none of these models have been like pre-trained on any large scale training data. And then there we show that this is the best architecture. But the even more surprising thing is, like, even when we consider all models which have this large scale pre-training data, like Pi 0 or Pi Groot N1 or Molmer, so this model is still very performant, like without any large scale pre-training. It's just fine-tuned on small amount of training data on that particular task. And we found it to be the second best, better than all Pi 0.5 or Groot N1 or Molmer, this simple design, showing that it's very effective. Let me like quickly go over the different components here. So here we have like a vision language model, VLM. The first thing we do to the VLM is provide it a system prompt where we say, analyze the input image and predict the robot actions for the next some X amount of time steps. And the actions itself are, as I said, was integers between 0 and 1000. Then it can take the usual VLM input. So it can take multiple camera images, single camera image as input. It can take then it can take the user prompt, the particular task. And it, just like predicting language, it will predict the action as language itself, right? So there is no new token or no action heads. It's directly predicting these numbers 0, space 12, 1, 2, space 9. So it's directly predicting those things as tokens. Okay. So that's the entire architecture of this method, and it's just fine-tuned on doing this task. And
how
not,
do you convert Ankit, how do you convert these numbers into the action?
Yes. So these numbers are essentially just a normalized value of the action itself. Because so let's take our SO100 as example. So it has, let's say we are predicting joint actions, and the joint actions are like 6. It would require a 6-dimensional action, and let's say we are predicting for 8 time steps, so it will have to predict this 48 floating points numbers, and these 48 floating point number each is scaled between 0 to 1000.
Oh, I see. Then you divide by 1000. That's your
Yeah,
actual number.
Yeah.
Okay.
Exactly.
Okay.
Exactly.
Nice.
And this could be anything. So like we could fine tune it with, let's say, 10,000 or any 100,000, depending on whatever kind of resolution we want. And similarly, the results on real. So it is outperforming this model called small VLA, which is from Hugging Face. And it has, the small VLA model is like specifically pre-trained on a large scale SO100 data. But our model is just fine-tuned on some 100 demonstrations for each task. And it can perform better than small VLA, showing that this design is really, really powerful. Powerful design, and it's like retaining the capability of the VLM well. The the method we just opened, so we just released the paper a couple of weeks back, and the more details about training would be there. So here I the key takeaways for us would be, what I showed was like hierarchical design of VLAs. So how we can take a VLM, how we can combine the strength of a VLM and a 3D policy. I went into 3D policies for a bit and showed you how one specific design of a 3D policy, and these are which are like very efficient at learning tasks, right? They can learn at very few demonstrations. And then among these monolithic designs, we what I showed about was about VLA 0, and showed that it can be very surprisingly very effective. Like this design, this simple design can be very effective, better than many pre-trained VLAs. Okay, so that would be it, and I'll be happy to take any questions.